So you guys did it as CO plus 3 plus 3OH minus, right? So that's how it breaks apart. What's this Ksp based upon? I mean, what kind of a solution do we have? So what type of solution do we have when we take this and mix it up? What kind of solution do we have to have when we start working with some things that deal with Ksp? Unsaturated or saturated? What do you think?
Unsaturated?
Be saturated. So all these are saturated.
Why?
They're the max. They're maxed out. Because we're not going to work with anything that's not maxed out, because it has a maxed out point. And we call that a saturated level. So at some point, we can't dissolve any more to these substances. So all these substances listed on page 643, they pretty much, if you put them in water the way they are, they won't dissolve. So any of these substances on page 643. Now if you put it in enough water, it may dissolve. But you have to really pump up the volume a lot before it will dissolve. Look at what metals don't dissolve well in water when they're mixed with, they're put with another substance. So I want you to look at some of the metals that are most characteristically on this table, 16.1, and you kind of look at the ones that could be harmful to you. Do you see any that could be harmful if you would intake those by drinking, or what do you think?
Mercury?
Mercury, yeah. Does mercury on there quite a bit? Chlorides it is. Iodide it is. Bromide it is. Carbonates. Do you think that's good? It has a very low solubility. Yeah. If it had high solubility, then we'd have it more in our drinking water in higher concentrations, and we probably would have health issues big time. Okay, what's another thing on there do you see that's could be harmful to us?
Cadmium.
Could be cadmium. I don't know much about cadmium. I know a lot about this other one. What? Lead. Lead's on there a lot. I'm glad lead is on there, mercury's on there, because that means even if it does get in your drinking water, what's the concentration going to be?
Very small.
Very small. Now, it could be big. It could be more if you eat. If you eat, a lot of times mercury is known to be in fish. And I don't know all the specifics about that, but it can build up its concentration in fish. So if you eat that, then there's a more likely chance of you getting more mercury in your system than if it's in the water. Because the water can only hold so much, and it won't hold anymore. So the next thing I'd like you to do is set up the Ksp expression, or what we call the solubility product expression for this. So if you need to look at an example, you can look at the top of page 642. So go ahead. The next thing I want you to do is write solubility product constant, or solubility product equation. Go ahead and set that up for this one. Does that look good? Okay, next thing I want you to do is set it up underneath and include your x's. So we're going to go ahead and solve for x, and every time you solve for x, you solve for the solubility. Every time you do a problem like this and you find x, it's just like always, like we've always done. That's the solubility of the solution. That's the maximum moles that can fit into a liter of solution at 25 degrees Celsius. So the next thing after you set that up, I'm going to have you solve for x, which is solving for the solubility. So it should look like this, and this is where students make mistakes. Because when you look at the above equation, when it breaks apart one part cobalt, 3 part hydroxides. So cobalt's going to be x, and hydroxide is going to be 3x. So now you got to solve for x. So go ahead and do that, and we'll see what you get, and then we'll go to the next type of problem.
What chapter was the Chatelier's?
The Chatelier's principle was on I believe it was chapter 13. Yep.
Thank you.
It's in page like 342. It talks about some things. 340 through 342.
Right, yeah, here it is.
You guys remember when we did our solubility rules, which ions were soluble and which ones weren't very soluble? You remember doing that? I want you to look on page 643. Look at the ones that are most commonly insoluble. What are they? The ones that have the largest number. Carbonates, hydroxides, sulfides. And if you remember, those are the ones that have a lot of insolubility, okay, associated with them. So when you figure that out, what is the simplification of this? What would that be? 27x to the fourth. Okay? And then what do you guys do? You just divide it by 27 and then take to the fourth root, and you should get an answer out. If I did it correctly, I'm hoping it is 9.8 to the minus 12. Is that right? Is that what everybody got? So you got to take this 2.4 times 10 to the minus 43rd. And you got to go to the fourth root, and it has to be divided by 27 first. You guys know how to do the fourth root? Okay. And I came up with 9.8 to the minus 12. So what is that? That's molarity of COOH. That's what it is. That is the solubility. That means in a liter of water you can dissolve 0.000000000098 moles of it. Not soluble. Okay? Extremely insoluble. Question you got on that? So then the next one is kind of reverse of this. So the next one's saying, hey, here's the solubilities. What's the Ksp? So what is this?
Do you just want me to sit under this?
Yeah. So what does this equal? The solubility, but what else does it equal in your equation? It equals, well, eventually you're going to have to use it to find the Ksp, but what does this equal? So I go back to this. What does this equal in this equation? What does this symbolize in this equation? X. This is X. So you're going to have to solve for the Ksp, knowing how that dissociates, and then plugging in X. And as you plug in X into your equation, you'll get your Ksp. So you got to do the same thing as we originally did. You have to dissociate it to see what the ratio is of your magnesium to hydroxide. You have to set up your equation based upon X. And once you do that, then you can plug in that concentration in for X and solve for the Ksp. So go ahead and solve for the Ksp of MgOH2, and the answer is on page 643. So you can check to see if you got your answer right by looking at the table on page 643. So go ahead and do that and see what you get. You can figure out that's how you just plug them in. And did you guys put them in as 4x cubed? Did you? And you got the same answer, right? Okay. The only reason I like this, sometimes it kind of shows me that it's doubling, you know. And that's why I just put it in like that, because I can actually see the concentration is double, and it makes sense to me. Okay. One last problem. I won't show you the last one because I think it's just going to take a little bit more time than we want to spend on it today. Okay. This is called what's called the common ion effect. So sometimes if they want to reduce an ion present in a solution, they'll introduce a different two solutions together. And when they combine two solutions together, they have what's called a common ion effect. The common ion effect, what it does is it takes and reduces the number of ions or how much of a certain ion can dissolve if they want to decrease the amount that will dissolve. So it's called the common ion effect. And these are really pretty easy to do when you do them. So, it says, what is the concentration of fluorine ions in a saturated solution of CaF2 when dissolved in a... I'm gonna change this. I'm gonna put, what's the concentration of CaF2? What's the concentration of C8? I messed up on this. So what is the solubility? Okay, that's what I need to ask. So apologize for not having it set up right. So what is the solubility of CaF2 in a saturated solution of CaFO2 when dissolved in 0.45 molarity solution of NaF? Okay, so what's common between, what ion's common between what we're trying to dissolve and what solution it's in? What ions are similar? Which one? Fluorine. So fluorine's similar in both. Okay? So when we set it, now CaF2 has a very low solubility to begin with. So when we look at the concentration of fluorine ions, this is going to be one like we said when we do do plus 2x type of thing. This one will be plus 2x, but we won't add the plus 2x because the x is going to be really, really tiny. And so it won't affect the 0.45 molarity. You can add the 2x to it, but it won't matter. Okay, so first of all, this NaF will dissolve, and when it does, it makes 1 Na plus 1 fluorine minus. Okay, so what's the concentration going to be of fluorine minus here? So this starts out to be 0.45 molarity. What's the concentration of fluorine? Same, right? Okay. So then we set up our expression, and it says Ksp of CaF2 is equal to calcium fluorine squared. Okay, I probably should just put not 2F, but just the fluorine concentration squared. Okay, I think I could get by by putting 2F, but I'm going to just put F.
Why are you doing it now and
I don't know if I did it on the first one. Did I? I did the 2X, but I don't know if I did the 2 fluorine on that first one. I didn't. Because I don't want to make it look like I take 3 times whatever the the concentration is going to be whatever it is for hydroxide. Okay? So that's why that I just leave it as that, and then when I want to go ahead and put it into here, I know it's a 3x. Okay? Because whatever the concentration they give me, I want to plug in there directly. I don't want to take it times 3. So there'll be some problems where they'll give you the concentration of the solution. You don't want to multiply by 3 because that's the concentration of the solution. You just want to cube it or square it. So that's why I don't do it. And that's why you shouldn't do it there. But when you set up to solve for x, that's when it would come into play. So then you would go x, 2x squared, right? Okay, so actually, I'm going to set this up, and we're just not going to worry about the adding on this, because when you set it up, it should be plus this 2x, and you'll see what I mean by that here in a second. Okay. So we have this one is going to be, guys, what is the Ksp for CaF2?
4.0 times 10 to the negative 11.
Minus 11. So that's going to equal your x.
4x to the cube.
Well, let's just wait before we do that. So I'm going to go x. And then you don't need to, if you want to write this down, you can. We're probably never going to use it. So then it's going to be 2, okay, then it's going to be, what is the concentration? 0.45?
Yep.
Okay, so 0.45 molarity plus 2x. Okay, I need to explain what I mean by that. So on the original, our solution had NaF, right? Okay, so on our original, we said that there was 0.45 molarity of fluorine, correct? Plus the 2x. what I mean is the 2x is what if you would do it normally, you would solve for x, and that would be 2x, and that would be your concentration of fluorine ions, and it's going to be really, really tiny. So when I put 0.45 molarity plus 2x, I can get rid of the 2x. Does that make sense? Because the 2x is going to be really, really tiny concentration. So it's like adding 0.000005, something really small. So what can I make this now? I can make it x. That's a long explanation to make this an easy problem. And then that would be what? This should be squared, right? That's going to equal 4.0 times 10 to the minus 11. Okay? I don't know if I explained that the best, but all I can tell you is that the concentration of fluorine ions are really huge compared to original solution if you didn't have that common ion in there. So what you do is you substitute in the molarity of the fluorine ions for your 2x. And then solve for x. So you got to solve for x. And it should be really small. Or it should be smaller than normal. But we'll see. So x is equal to 4.0 times 10 to the minus 11th divided by 0.45 molarity squared. What did you guys get?
1.98 times 10 to the negative 10.
Negative 10? Okay. And it would be what now again?
1.98.
1.98.
98.
That's the molarity concentration of CaF2. If we would have done this and it was in just water, that would be a lot higher solubility. So you should be able to see why sometimes they use common ions to eliminate bad ions like silver and mercury and lead, because they're bad ions. And so what they'll do is they'll add a good ion that's part of what can precipitate out, and they'll add it, and it won't have an effect on you, and so that'll be good. Okay. This assignment, this will be our last, basically, problem assignment that you guys will have. So, and I've got, one of these questions deal with something I didn't get to today. So, this is on page 663. Man, that's a lot of pages we went through. 660, we went through every chapter, so we went through 663 pages. 23B. Now all these you can check your answers on. So check your answers. And this is all the problems we'll do on this chapter. So, all these problems, we won't do anything else more in this chapter. There's one I have to show you yet, but I didn't have time to do it. Some of you got a test that you got to take. So I'll be here 9th period. Okay, you can take it then. And I've got those graded. I can give those back on Monday, probably, to let you look them over.
When is the retake?
I can be next week or something. Yeah. Okay. I hate doing these discussions on Friday and that, but we're to the point we're almost done. We just got electrochemistry to do after this, and that'll take 3-4 days. Do an experiment in there or two, and then you guys will work through practice AP exams. You can work through AP exams and that, because that'll be 2 weeks from yesterday. You guys are doing that. They're taking it. And they will have electrochemistry stuff on there, and solubility products, they have those on there, and that type of thing.